All right, this is going to be our walkthrough for the homework assignment titled Extra Integrals Review. And so we're going to start right off here with using the Fundamental Theorem of Calculus to find the derivative of this integral expression. So just like we did when we did the assignment with these, we're gonna let capital F be an antiderivative of that function that's inside of the integrand. So cosine t over t squared plus 2. And so effectively then, if we want the derivative of this, because that's what it's asking us to do, right, then that should be the derivative of the integral of that function evaluated from x cubed to 5. Well, the function now, that is the function that's the integral of that, is just capital F. So we'll evaluate that at 5 and x cubed. And so now when I take the derivative of capital F of 5, well, capital F of 5 is a constant, and thus its derivative is 0. So really all we've got is the derivative of the opposite of capital F at x cubed. Well, in order to take the derivative of something that is a function within a function, we have to do, it's still a negative sign in front, it's the derivative of capital F evaluated at x cubed, and then we have to multiply that by the derivative of x cubed, which is 3x squared. So we end up with a negative 3x squared times the original function, because it's the derivative of capital F, evaluated at x cubed. So that'll be times the cosine of x cubed, and then all divided by x cubed squared, which would be x to the 6th, plus 2. And that's our final answer. We'll use the same process here. Now we're just doing the integral from sine of x to cosine of x of t squared. Now we know what the integral of t squared is, but remember that we're looking for the derivative of this, so it doesn't really matter what the integral of this. We'll just call capital F the antiderivative of t squared. And so we end up with the derivative of capital F of cosine x minus capital F of sine x. Well, we know that the derivative of capital F is just t squared, right? So this just becomes the original function, t squared, evaluated at cosine x, times the derivative of cosine x. So that'll be negative sine x times cosine squared x. And then we'll subtract from that the derivative of sine x, which is cosine x, right? That's the chain rule part still again, times sine squared x. And of course, if you want to, you can factor a sine x cosine x, or even a negative sine x cosine x out of those, but this answer is perfectly acceptable as well. For our next one here, same thing. We'll just say that capital F is an antiderivative of the cosine of 5t. Now, of course, we could integrate cosine 5t, but we don't really need to for this problem because we just want to find the derivative of this. So this is the derivative of capital F of x to the 5th minus capital F of x cubed. So we'll just do the chain rule, right? It'll be capital F prime of x to the 5th times 5x to the 4th. So 5x to the 4th. And then our original function evaluated at x to the 5th, which is cosine of 5x to the 5th, and then we'll subtract from that the derivative of x cubed, which is 3x squared, times the cosine of 5x cubed, right, the cosine of 5t. And if you want to factor out a common term there of x squared, you can, but I don't need you to do it. All right, for our next one here, we're just going to use part 2 of the Fundamental Theorem of Calculus to evaluate the integral. So really what we're doing here is we're just integrating and evaluating what this is equal to, right? These are just definite integrals. So if I integrate cosecant squared theta, that's just negative cotangent theta, right? That's just one of our integral rules, right? We have the integral of negative cosecant squared is cotangent. So if I don't have the negative, it must be negative cotangent. and we'll evaluate this from pi over 6 to 5 pi over 6. So we've got negative cotangent 5 pi over 6 minus negative cotangent, so plus cotangent of pi over 6. And well, the cotangent of 5 pi over 6, you should know that that's negative root 3. So what we've got is negative of negative root 3 plus, and then the cotangent of pi over 6 is just root 3. Right, so we've got negative negative root 3, which is root 3 plus root 3, gives us 2 root 3. Same process here for this one. We're just going to integrate this and then evaluate on that integral. So the integral of 4 is 4x, and the integral of 1 over x is natural log absolute value of x. So we'll evaluate this from 1/3 to 5, and that's going to give us 20 plus ln 5 minus 4/3 plus the natural log of 1/3. And 20 is 60/3, so subtract 4/3, that's going to be 56/3 plus ln 5, and then minus ln 1/3, right? Minus ln 1/3, that's like just the ln of 1/3 to the negative 1. Well, that's just the ln of 3, so we've got plus ln of 3. For this next one, we're just going to do the same thing. We're just going to integrate. Both of these pieces we'll just integrate using the power rule. So 4x to the negative 5 will go up to 4x to the negative 4, and then we'll divide by the negative 4. So that just gives us negative x to the negative 4. And then negative 5x to the 4th will go up to negative 5x to the 5th, and then we'll divide by the 5, so that'll just become minus x to the 5th. And we just want to evaluate this from 1 to 2. Now, negative x to the negative 4th is just negative 1 over x to the 4th. So when I plug in 2 to that, that's negative 1 over 2 to the 4th, which is 16. So negative 1/16. And then minus 2 to the 5th, which is 32. And then we'll subtract from that what we get when we plug in 1 to those. And so if we plug in 1 to both x to the negative 4 and x to the 5th, those are both just 1. So it's negative 1 minus 1. And if we combine all that together, really that's just negative 1/16 minus a negative 2. So minus 32 and then minus the negative 2. So that's minus 30. And getting a common denominator there and combining those together is just going to turn that into negative 481 over 16. For our next one here, we're going to do same thing. We're just going to integrate and evaluate from a to b, from 4 to 9. And so in order to integrate this, this is one of the ones where we have a single term in the denominator, and we can just divide everything in the numerator by it. So this becomes an integral from 4 to 9 of t divided by the square root of t. Well, that's t to the 1st over t to the 1/2. That's just t to the 1/2. And then minus 3t to the negative 1/2. And now when we integrate, t to the 1/2 will become 2/3 t to the 3/2, and minus 3t to the negative 1/2. T to the negative 1/2 will go up to t to the 1/2. When we divide by half, that's like multiplying by 2. So we end up with 6t to the 1/2, or 6 root t. And we'll evaluate that from 4 to 9. So we'll start off with 2/3 of 9 to the 3/2. Well, 9 to the 3/2, we square root the 9, that's 3, and then cube it is 27. So 2/3 of 27 minus 6 times the square root of 9, so that'd be 6 times 3, or 18. And then we'll subtract from that what we get when we plug in 4 to this, which will be 2/3 times 4 to the 3/2. So 4 to the 3/2, you square it to 4 to get 2, and then cube it to get 8. So 2/3 of 8 minus 6 times the square root of 4, so minus 12. And then we'll just combine things together there. the 27 over the 3 is 9, so that just ends up being 18. And then we have another, this is 18, and then minus 18, so those just cancel out. So we end up with a positive 12 over here when we distribute that negative sign through, and then minus 16 thirds. So really, it's just 12 minus 16 thirds, which would be 36 thirds minus 16 thirds, which is just 20 over 3. And this one will be basically the same process here. We're just going to divide both of the terms in the numerator by that square root u. So this becomes an integral from 0 to 4 of 1 over root u, or u to the negative 1/2. And then root u over root u is just 1. And so now we'll integrate the integral of u to the negative 1/2. We've seen this one a few times, right? It goes up to u to the 1/2, or square root of u, and then you multiply by 2. So this is 2 root u minus u, evaluated from 0 to 4, which just gives us 2 times the square root of 4. 2 times 2 is 4, and then minus the 4, and then minus 0 minus 0, which all just comes out to be 0. So the next few problems were evaluating indefinite integrals. And for this first one, we're going to do a u-substitution because we have a function that 2x squared within the cosine. So we're going to let u equal 2x squared so that du is 4x dx. And in order to get a 4x in there, we just have to multiply by a 4 on the inside and a 1/4 on the outside. So we have 1/4 of the integral of the cosine of u du, right? And the du comes from the 4x dx, because that's what we said du was if u was 2x squared. And so now we'll just integrate cosine of u. So this is 1/4 of the integral of cosine is sine. So this is just sine of u plus some constant. And then when we distribute the 1/4 through, we have 1/4 the sine of, and we'll replace the u with 2x squared. So 1/4 sine of 2x squared, and then plus some constant. This next one is also going to require u-substitution. The function within the function is the 1 minus r cubed, so we'll let u equal 1 minus r cubed, and du will be negative 3r squared. But we don't quite have negative 3r squared. We do have 9r squared, so we can turn that 9r squared into a negative 3r squared fairly easily. We can put a negative out in front and a negative inside, and then we can turn that 3, or that 9, into a 3 times a 3r squared. So this integral is exactly the same as the integral we started with. We just put a negative inside and a negative outside. And so now we can pull the 3 that's in here outside if we want, leaving us with a negative 3 outside of our integral. And now we have the negative 3r squared dr that turns into the du. And then we have over the square root of u, which is just like negative 3 times the integral of u to the negative 1/2 du. And so now we can just integrate that. If we integrate u to the negative 1/2, that goes up to u to the 1/2. And we'll divide by 1/2, so that becomes 2 times u to the 1/2 plus some constant. And we'll replace the u back in there. And we can distribute that negative 3 through, so we get negative 6. U to the 1/2 is a square root, so square root of 1 minus r cubed plus some constant. For our next one here, there's not really a good substitution to do with the sign. So what we need to do is we need to rewrite this in terms of another trig function. So this can be rewritten just as cosecant squared 3x dx, because we know that the integral of cosecant squared is negative cotangent. And so now we do have to do a u substitution for the 3x. We'll let u equal 3x, and then du will be 3 dx. So we'll want to put a 3 inside of our integral and a 1/3 outside of the integral, which turns this into 1/3 of the integral of cosecant squared u du. And now we can integrate that using the rule that we know, that the integral of cosecant squared u is negative cotangent u plus some constant. And then we'll just replace the u with 3x and distribute the 1/3 through. So we get negative 1/3 cotangent 3x plus some constant. For our next one here, again, this one, we could use a substitution on cosine, but it's easier if we notice that sine over cosine is tangent, and then we'd have a 1 over cosine left, which is secant. So we can rewrite this as secant of 2t plus 1 times tangent of 2t plus 1. And if we do that, then we know that the integral of secant u tangent u is just secant u. So we'll let u equal 2t plus 1, and then du will be 2 dt. And so if we have that, we just need to throw a 2 inside of here to give us the 2 dt with a 1/2 out in front. So we have 1/2 of the integral of secant u tangent u du. And the integral of secant u tangent u du is just secant u, so we have 1/2 of secant u plus a constant, which is 1/2 the secant of 2t plus 1 plus some constant. For our next one here, we've got a square root of tangent x times a secant squared of x. And so we'd want to note that the derivative of tangent is secant squared. So if I let u equal tangent x, then I've already got the du built in, right? Du will just be secant squared x dx. And so this just ends up being an integral of the square root of u, or u to the 1/2 du. And that can be integrated to become 2/3 u to the 3/2 plus a constant. And then we just replace the u with tangent. So we have 2/3 of tangent of x to the 3/2 power plus a constant. For our next one here, we've got cotangent 3x in the denominator, so dx over cotangent 3x, which, well, 1 over cotangent is the same thing as just tangent. So this is equivalent to the integral of tangent of 3x dx. And we proved in class what the integral of tangent is. If you don't remember it, though, you can always rewrite this as sine over cosine if you want to. But that's just up to you. I'm going to just use the rule that we proved in class because I think it's good for you to know it. We'll let u equal 3x, and then du will be 3 dx, so that we can turn this into an integral that's just tangent u. So we'll put the 3 inside and the 1/3 outside, like I just did. And we have 1/3 the integral of tangent of u du. Well, in class, we proved that the integral of tangent is negative natural log absolute value of the cosine of u plus some constant. So we can just use that rule. If you don't remember that rule, remember you can just rewrite tangent as sine over cosine and do a u substitution for the denominator for the cosine. You'll end up getting this exact same thing. And sometimes you see it written as natural log of the absolute value of secant, which is also fine. So here we have negative 1/3 natural log absolute value cosine of u, which was 3x, plus some constant. For secant to the 4th of x dx, we're going to have to get a little bit creative using some trig identities here. So first we'll rewrite this as just secant squared x times secant squared x, because we know the trig identity that 1 plus tangent squared is equal to secant squared. Right, and I also know that the derivative of tangent is secant squared. So if I rewrite this as 1 plus tangent squared x times secant squared x dx, then I can do a u substitution for tangent. And if I let u equal tangent x, then du is just secant squared x dx. And I can replace the tangent squared with u squared and the secant squared x dx with du. So this becomes an integral of 1 plus u squared du, which is u plus u cubed over 3 plus some constant. And then we'll just replace the u's with tangent, giving us tangent x plus tangent cubed x plus some constant. For our next one here, for dx over x ln x, we want to look at that and realize that the derivative of natural log of x is just 1 over x. So if I let u equal the natural log of x, then du, which is 1 over x dx, is already built into there, and I've got the x in the denominator. So this can just become the integral of du, that's the dx over x part, and then over natural log of x, or just over u. And we know what the integral of du over u is. It's the natural log of the absolute value of u plus a constant. So this just becomes the natural log of the absolute value of the natural log of x plus a constant. All right, so our last few here, we're just going to go back to doing some definite integrals. So this first one here, we want the integral of tangent squared secant squared. And remembering that the derivative of tangent is secant squared should allow us to just let u equal tangent x. And if u is tangent x, then du is secant squared x dx. So that'll let us replace the secant squared x dx with du. And of course, we need to convert our limits of integration. So if x is equal to 0, then u is also equal to 0 because the tangent of 0 is 0. And if x is equal to pi over 4, then u should be equal to 1 because the tangent of pi over 4 is 1. So this integral should become the integral from 0 to 1 of u squared du, right? The tangent was u, so it's u squared. And then the secant squared x dx becomes du. And so now we don't have to even worry about converting these back into x. Once we're done, we just take our integral, u cubed over 3, and evaluate it from 0 to 1, which just gives us 1/3 minus 0, or just 1/3. And it's really nice when we do the u sub to convert into terms of u for everything, including the limits of integration, so that we don't actually have to convert back to x in the end. All right, for our next one here, we're just going to do a u substitution for that denominator because if you think about that, the derivative of x squared plus 1 is 2x, right? And so if I let u equal x squared plus 1, I've almost got my du in there already, right? I just need to put a 2 up there and a 1/2 out in the front. Right? Those cancel each other out, and it gives me the du inside of there. So this ends up becoming 1/2 of an integral of du over u. And we do need to convert our limits of integration. So when x is equal to -1, u should be equal to -1 squared, which is 1, and then plus 1, which is 2. And when x is equal to 3, u should be equal to 3 squared plus 1, so 9 plus 1, which is 10. So our new limits of integration are just going to be from 2 to 10 on this. And then we'll just integrate. This is now 1/2 of the natural log of the absolute value of u, evaluated from 2 to 10, which is just 1/2 of the natural log of 10 minus the natural log of 2. We can ignore the absolute values now because both 2 and 10 are positive. Natural log of 10 minus natural log of 2, that's the same as natural log of 10 over 2. Which is natural log of 5. I'd probably write this as 1/2 the natural log of 5. If you left it up here like this, that'd be fine. This would be good. You could bring the 1/2 inside as a square root. You could write natural log of root 5. Any of those answers would be fine. All right, for our next one here, we'd want to recognize that what's inside of the square root, if we take its derivative, we actually get the rest of our integrand. So we want to let u equal the stuff inside that square root, t to the 5th plus 2t. And if we have t to the 5th plus 2t, then du should just be the 5t to the 4th plus 2 dt, which we've already got. So this just becomes an integral of the square root of u, or u to the 1/2, du, right? Because the t to the 5th plus 2t is u, it's inside the square root, and the 5t to the 4th plus 2 is outside of it. That's our du. And we do need to change our limits of integration, right? So when x is equal to 0, u is also equal to 0, right? Because 0 to the 5th plus 2 times 0 is still 0. But when x is equal to 1, then u should be equal to 1 to the 5th plus 2 times 1, or 1 plus 2, should be equal to 3. So our new limits of integration here are going from 0 to 3. And so we'll integrate. That gives us 2/3 u to the 3/2, evaluated from 0 to 3, which is going to give me 2/3 of 3 to the 3/2. So that's going to be the square root of 3, and then I'm going to cube the square root of 3, so that'd be 3 root 3. And then minus 2/3 times 0 to the 3/2, which is just 0. I can cancel the 3's in the first part of it and just end up with 2 times the square root of 3. And just 2 more to go. For this one, we always want to try and substitute out that denominator if we need to do a substitution. And so if we try to substitute out that whole denominator as u, if we let u equal 3 plus e to the x, we should see that du is just e to the x dx, which works out perfectly because that's exactly what we have in our numerator. So we do need to convert the limits of integration. When x is 0, u is 3 plus e to the 0, which is 4, right? 3 plus 1. And when x is 2, then u is 3 plus e squared. So not that great of a number, but that's fine. So we'll just rewrite this integral as du over u, the integral of du over u, evaluated from 4 to 3 plus e squared. Right. And so now we can just integrate this. This is natural log absolute value of u from 4 to 3 plus e squared. The absolute value is not going to matter for this because both of those are positive. So we have natural log of 3 plus e squared minus natural log of 4, which would be fine. Normally, I'll rewrite this as 1 logarithm, so the natural log of 3 plus e squared over 4. Since it's the natural log of a minus b, or natural log of a minus natural log of b, it becomes natural log of a over b. And that's our final answer. All right, for our last one here, we have dx over root x times root x plus 1 cubed. This one might be a little bit tricky to look at first, but we don't really have to worry about that cubed, right? Because if I let the thing inside of it be u, so if I let u equal root x plus 1, then I would just have something over u cubed, which is easy enough to integrate, except I'd still have that root x. Well, du, if u is root x plus 1, du is 1 over 2 root x. Well, I have the 1 over root x in there already, times our dx, of course. So I just really need to put a 2 down there. If I put a 2 in the denominator, I need to cancel it out with a 2 in the numerator, or just multiplying by 2 out in front. So now we end up with 2 times an integral of the dx over the 2 root x is just a du. And then the 1 over root x plus 1 cubed is 1 over u cubed, or u to the negative 3. And we do need to change our limits of integration. So when x is equal to 1, u is equal to the square root of 1 plus 1, or 2. And when x is equal to 4, then u is equal to the square root of 4, which is 2, plus 1, so 3. So this becomes an integral from 2 to 3 of 2u to the negative 3. And if we integrate u to the negative 3, that goes up to u to the negative 2, and then we divide by the negative 2. So it's negative 1 over 2u squared, because we're dividing by the 2. And we're going to evaluate that from 2 to 3. Now, clearly the 2's can cancel out there. So really this is just like negative 1 over u squared from 2 to 3, which will be negative 1/9 minus negative 1/4, or negative 1/9 plus 1/4. If you get a common denominator on that, that's negative 4/36 plus 9/36, which gives you 5 over 36. And that's the end of this walkthrough for this homework assignment.